The Future History of Energy and Transportation. Documenting the paradigm shift from the era of oil and internal combustion to the era of robotics. By Julian Cox. Narrated by the author with the aid of an artificial intelligence. Chapter 11. Societal Level Energy Efficiency Explored. Comparing real-world vehicle-level energy efficiencies between vehicles of similar and differing drivetrain technologies is profoundly useful by comparison to discussion of component-level energy efficiency, as if differences on the bench translated directly to efficiency felt by a customer, let alone society as a whole. Vehicle-level energy efficiency is highly applicable to vehicle customers and users. Naturally, depending upon the cost of the appropriate fuel or energy source, the likely fuel or energy costs of moving a vehicle can sensibly be derived from miles per gallon or watt-hour per mile metrics and similar volatility in fuel markets and driving habits permitting. Nevertheless, vehicle-level energy efficiency is arguably just as misleading in common usage as component-level efficiency, when used to imply the resulting energy efficiency is felt directly by society at large. Because contrary to received wisdom, this is not true. The objective here is to define societal level energy efficiency and choices in a way that makes sense and rings true because it is true. When we are talking about energy efficient technology choices for society, what we want to be efficient about is vehicle miles for transporting passengers and their luggage. Hence, societal level energy efficiency, the bottom line. We can ignore the chemical energy content of fuels or batteries. We can ignore what happens within the vehicle, including any of its components, so long as it is filled up with whatever it is supposed to be filled up with, ready to transport passengers and their luggage a certain number of miles. Then all we need to know about energy efficiency from a societal perspective is how much energy, per mile deliverable, was expended by society to get the vehicle into that condition, ready to deliver miles. Energy expended to prepare the vehicle to deliver the miles, divided by vehicle miles deliverable, in watt-hours per mile. That's it. So long as the vehicle delivers the miles without some abnormal compromise to privacy, convenience, comfort or safety, and we are talking strictly about energy efficiency and not emissions, what a vehicle does internally beyond delivering the miles to the passengers, is an irrelevance. Once the energy is in the tank or the battery, in energy terms it has passed beyond reach of rational concern for society. It has passed beyond reach of rational concern because the sum of all societal efforts has at that point been fully transacted from the account of society as a whole, to the account of mileage of the vehicle. With a gasoline car we know this to be true because this is when the credit card gets swiped at the fuel pump. After that, the user is principally concerned about how many miles they can travel before returning to a pump. The same goes for any other fuel, be it gas, liquid or even solid, electrons or none of those things. The role of society in energy ends in that transaction, and the vehicle user's role in consumption of mileage, not energy, is commenced. In an electric vehicle the line is a little more blurred, but not much. Disregarding the fact that the customer can readily move the entire energy transaction to their own account, by self-generating electricity, thus standing on the society's side of the equation as an energy producer, in energy terms it is blurred because there is a significant extra charging efficiency transaction that occurs between the card being swiped at the electrical outlet, and electrical charge actually accumulated in the battery. This charging efficiency loss is more significant in energy terms than the odd drip of spillage and the effects of fuel evaporation upon tanking a gasoline or diesel vehicle, while hydrocarbon tanking emissions are significant in emissions terms. To maintain focus on topic, energy efficiency, charging losses between an electrical outlet and a battery, is more significant. Deducting both typical charger losses and the charging efficiency of a traction battery, introduces a factor of nominally 10% such that 111 kilowatt-hours at the outlet will result in a 100 kilowatt-hour battery charge. In the previous chapter we looked at the example of the Tesla Model S, that calculated from US EPA figures requires 113.4 kilowatt-hours for a full 100 kilowatt-hour charge. Charging losses may be moderated with direct DC charging. However, typically DC charging operates at very high power, which extenuates ohmic charging losses in the battery to compensate for the absence of an AC to DC battery charger in the loop. Nevertheless, the societal role in delivering the energy ends at the electrical outlet, and the account of vehicle mileage absorbs any charging loss. Hence, in all practicality, while charging losses is a finer point of physics not to be missed in other contexts, in the context of societal level energy efficiency, what we care about is how many miles are deliverable, in return for electricity transacted at the electrical outlet. So to recap, from a societal perspective, what we are looking for is not the energy contained in the fuel nor the energy contained in the battery, but the energy expended in getting the fuel from wherever into the tank and alternatively, getting the electricity from wherever to the electrical outlet, in sufficient quantity for passengers to travel a mile. A figure of merit would therefore be societal energy efficiency of transportation per mile. The better that efficiency is, the more transport is received by passengers, or in aggregate society as a whole, in return for expenditure of societal energy resources. Perhaps disparagingly for some, obtaining passenger mileage from the energy expended in retrieving oil and processing its products to the pump, is quite efficient, on an energy basis per passenger mile. This is self-evidently true, and here's why. If all one had to do was to place a wide funnel into the tank of any gasoline car and leave the car with its funnel outside overnight, while it rained gasoline, then the societal energy efficiency of transportation would effectively be 100%. The societal energy cost per mile if it rained gasoline would essentially be 0 kilowatt-hours per mile and $0 per mile. The vehicle level efficiency of the vehicle would make no difference so long as the supply of gasoline rain was ample. From 0 kilowatt-hours per mile and $0 per mile, to the fossil fuel industry as it actually is, society is obliged to explore, drill and pump crude from the ground, transport, refine, transport and pump fuel to the tank. Nothing more. Except in the case of hydrogen produced from renewable energy, society is not obliged to supply the energy to drive a vehicle to the fuel. Mercifully, what we do have pouring down from the sky is not gasoline or diesel by night but photons by day, and photons happen to be a form of pure massless energy, just like electricity. Creating a form of passive funnel to capture photons as electricity, a solar panel, is entirely practical, but that is a matter for infrastructure level efficiency. If one were to be a purist about energy efficiency, it could be noted that a 23% efficient solar panel was as inefficient at the front end as a typical 23% efficient gasoline engine is at the back end. However, society is not a contributor to the energy content of either the sun in the sky, nor oil in the ground, and hence for societal level energy efficiency, the point is moot. What matters is those efficiencies that are a question of human agency and hence economics, choice, opportunity cost and labor. So if free gasoline from the sky would increase societal energy efficiency to 100%, what is a good approximation for actual societal energy efficiency in kilowatt-hours per mile for gasoline, and how does that compare to the available alternatives when driving on societally generated energy? A simple way to answer this for gasoline is to break the rules, mildly, which is to use emissions as a proxy for energy efficiency. The US DOE has published figures of 8.9 kilograms CO2e per US gallon of gasoline, as purely tailpipe emissions, and the figure at the root of DOE figures spanning the US EPA and NREL, for well-to-wheel gasoline emissions is 11.13 kilograms CO2e per US gallon of gasoline. Leaving a balance of 2.23 kilograms CO2e that has nothing to do with driving the car, and everything to do with getting the gasoline from the well to the tank. Note, the E in CO2e stands for CO2 greenhouse gas equivalents, so for example some CH4 or NOx. It's here to be faithful to NREL reference material. It gets interesting in the context of processes with a lot of fugitive CH4 emissions. In this context it is good enough to ignore it. 2.23 kilograms CO2e is almost exactly 25% of 8.9 kilograms CO2e, corresponding to the total tailpipe CO2e emissions, of 1 US gallon. We know 1 gallon is 33 kilowatt-hours in energy terms, so 25% is 8.25 kilowatt-hours, and 1/27th of that in a 27 miles per gallon fleet average new car, would give us a societal energy efficiency of gasoline of 306 watt-hours per mile. The current global fleet average gasoline car is probably not very far off the 27 miles per gallon US new car average, presuming the average car outside the US is a bit smaller than the US fleet average car, which is supposed to be 24 miles per gallon as at 2019. So there. Probably can't get much closer to the truth than that, plus minus 10%, by any means on any research budget, 306 watt-hours per mile for gasoline, 30.6 kilowatt-hours per 100 miles just to change the units to match those published by the US EPA. From a pure societal energy efficiency perspective, this is the energy expended by society to get a BMW 328i, a base Tesla Model 3 size and performance vehicle of roughly similar retail price, to deliver vehicle mileage. How about an EV? We have good figures for the Tesla Model S. The 2021 Tesla Model S has an EPA rating of 28 kilowatt-hours per 100 miles, and despite pointing out earlier that there is technically a charging loss between socket and battery, this is actually an EPA fuel economy, cost efficiency, figure, not strictly an energy efficiency figure, and hence it is measured at the electrical outlet taking the charging losses into consideration. This is 280 watt-hours per mile, just to change the units. All of this is supplied from society, assuming those who own private solar or wind installations are counted literally as productive members of society, in energy terms. The Tesla Model 3 requires 0.26 kilowatt-hours per mile and the Tesla Model Y 0.27 kilowatt-hours per mile, according to the US EPA. So in pure societal level energy efficiency terms, that's the number for the Tesla Model S. 0.280 kilowatt-hours per mile for a Tesla Model S driving on sunlight from the sky or from the grid versus 0.306 kilowatt-hours per mile for a BMW 328i driving on oil from the ground. At the first time of writing, the 2016 Tesla Model S required 0.350 kilowatt-hours per mile and the Tesla Model 3 and Model Y did not yet exist. Even so, the point remains well worth illustrating. From a societal perspective, 280 watt-hours per mile is only an 8.5% energy efficiency improvement over the 306 watt-hour per mile US fleet average new vehicle. The US fleet average 27 miles per gallon new vehicle certainly burns more energy than that, in the order of 1,248 watt-hours per mile. But from society, only 306 watt-hours is required to supply each 1,248 watt-hours to the pump. Tree huggers be like, the hell just happened? This is what just happened. Energy efficiency in terms of energy consumption per mile to society is, or was, not the correct argument for electric vehicles. This is why energy efficiency has been the wrong answer, and claiming otherwise, as has invariably been the case made for electric vehicles, has resulted in skepticism rather than the universal epiphany owed to anything that genuinely delivered a 25% to 85% efficiency gain on a societal scale. The new figures of 280 watt-hours per mile for the Tesla Model S, 270 watt-hours per mile for the Tesla Model Y and the 260 watt-hours per mile for the Tesla Model 3, is definitely a watershed moment, and it could be considered pretty significant in prospect to save roughly 10% of all energy used in passenger vehicles, or to gain roughly 10% more miles society-wide for free in energy terms. That is a lot of miles. What it isn't is anything like the disparity of roughly 25% to 85% often quoted, relating to comparative drivetrain efficiencies on a bench. Reviewing the calculations used for the infographic at the head of this section, we budgeted a matching 306 watt-hour per mile from society. 7% grid losses were applied to the electrical pathway to arrive at 284.58 watt-hours supplied to the electrical outlet. This is ample to supply every 2021 Tesla vehicle except the Tesla Model X large SUV. Again, this is a watershed in societal level energy efficiency terms for electric vehicles operating on the fungible electrical energy resources of society, one that has previously not been breached in a century. What is more remarkable is that this is not at all the most significant watershed in connection with these vehicles to be explored. So coming back to what just happened, there are opportunities for fossil fuels to seek to regain competitive dominance on this metric: societal level energy efficiency, mild hybridization, start-stop, pre-spun turbochargers with small engines, better aerodynamics, and so on. These options are readily available due to a historic lack of effort to do a better job. Recent efficiency rules with Formula One racing has yielded a technology called Tji Turbulent Jet Ignition. This is in essence a case of moving the spark plug to a small direct injected fuel air chamber on top of each cylinder head, to concentrate a rich ignition mix required for the functioning of a spark plug. This in turn functions as a hot plasma ignition system for the main cylinder containing the piston. The result is an engine that overall can run extremely lean with far more complete combustion than can be achieved with a point source spark in the main cylinder. Component level thermal efficiency of these TJI engines, that win Formula One races, is said to be greater than 47%. Although of course this will be somewhat attributable to running the engine at much higher temperatures than is reasonable for road use, or tolerable for low-cost materials from which to make engines designed to go hundreds of thousands of miles, instead of just surviving one race. Nevertheless, this is effectively a potential doubling of the component-level energy efficiency of a traditional gasoline engine, primarily in return for a minor rearrangement of the spark plug location from where Edward Butler put it in 1884. Any internal combustion engine manufacturer could retool for this at trivial cost and produce engines of this type with existing skills and production equipment. Moving auto industry incumbents in directions like this is the technical explanation why emission standards imposed by regulators from the 1990s to the present have proven counterproductive to the reduction of global emissions, corresponding to a global fleet doubling and a 60% increase in global emissions. Such regulations make fossil fuels more market competitive with renewable energy and electric vehicles, on the basis of both initial purchase price and running costs, in relation to small economy vehicles, seeding a boom in volume production. For electric vehicles, there are some component-level efficiency gains to be made at the charger, motor, inverter and in the round-trip efficiency of batteries. However, these and the aerodynamics at the vehicle level are already highly optimized, unlike the readily available efficiency gains for engines. More important than component-level efficiency gains when it comes to electric vehicles, is rapid gains in economies of scale and manufacturing efficiencies, exposing inherent cost savings in the production of far less mechanically complex machines. EV energy cost per mile is already significantly lower than the cost of gasoline mileage, but this is not as a result of gross disparities in societal level energy efficiency. Instead, the large differences in cost are attributable to vast disparities in labor and materials efficiencies in the supply of gasoline versus the supply of electricity. Not large differences in the use of fungible energy resources of society. Finally, the one really extraordinary thing about the close equivalence of societal level energy efficiency of transportation, contrasting internal combustion with electric vehicles, is that assuming as a society we were able to divert all 0.306 kilowatt-hours per mile used to power the fossil fuel industry, only as far as the pump and no further, as it pertains to passenger vehicle transportation. Meaning the 0.306 kilowatt-hours per mile well to pump is a combination of diesel fuel, bunker oil, electricity and so on expended to extract between 4 and 5 gigatons of crude oil every year and deliver gasoline to the pump. Those same 0.306 kilowatt-hours per mile is adequate to deliver all of the passenger miles that gasoline does, globally, assuming the global passenger vehicle fleet was electric, making the production of gasoline surplus to requirements for combustion and available instead, to produce gigatons of things. Meaning the energy content of the gasoline produced is not actually required to satisfy the market for passenger transportation in addition to the energy currently expended by society on the industry that produces it. Because opting for the choice of diverting the same 0.306 kilowatt-hours per mile in electrical form to charging electric vehicles, directly, instead of powering a precursory step of mining, refining and delivering fuel, means that the passengers and their luggage will have already arrived.